Up next, we have Nirvana Pillay and Edgar Jembere, and they'll be presenting their paper titled Future Frame Prediction in Transformation Space Using Good STN. Pillay, are you ready?
Yes, I am. I'm just going to share my screen quickly.
Okay, please do. So again, you have 12 minutes.
Okay, thank you. Okay, so hi, I'm Nirvana, and I'm a master's student at the University of KwaZulu-Natal, and my supervisor is Dr. Edgar Jembere. So today I will be discussing my research with you, which is entitled Future Frame Prediction in Transformation Space using the good STN. So what exactly is future frame prediction? So if we consider the machine learning model in figure 1, we see that it receives I context frames and is tasked with predicting the following J future frames, which means the model would have to analyze the input frames, derive patterns within those frames, and thereafter use those to predict the following frames. As such, it would need to model the temporal relationships within the data as well as the spatial aspects. The main challenge associated with this problem is that the future is inherently uncertain. The model would never be able to, with 100% certainty, tell you this is what the future will be. At best, it can give you an idea of what the future could look like. As more frames are predicted further into the future, the solution space diverges, resulting in a multimodal solution. What this means is that for a single set of context frames, there are multiple corresponding sets of future frames. Each set is equally as plausible and equally as realistic. So if we take the frames in figure 2, we see that between frame T and T plus 1, the actor's arm is moving in an upward trajectory. After frame T plus 1, the actor's arm may move downwards or may continue to move upwards, but at a different velocity. The actual ground truth, frame T plus 2, shows that the actor's arm did indeed move upwards, but that does not negate the validity of the other two motions. They're still physically possible and they're still realistic. So as these frames are generated further into the future, the degree of photorealism decreases in the sense that the frames become blurred and motion is underrepresented. This is more likely to happen if you generate frames from raw pixel values, as opposed to generating frames from predicted affine transformations. So in the transformation space, you basically take the adjacent frames of a video, extract the transformation between them, and thereafter predict a transformation and apply to the last frame of the input sequence. As a result, the model would only need to store information pertinent to transformations, transforming one frame to another. And as such, the learning process is potentially stabilized. And a further consequence is that only the edges of the objects are transformed, so spatial relationships are preserved. In this work, the spatial transformer network, the STN, was considered. It calculates transformations over the entire frame, including the static areas of the frame. So in summary, when conceptualizing a solution to perform future frame prediction, the following is needed: a spatiotemporal model, a suitable loss function, a decision on whether to predict frames from raw pixel values or in transformation space. And if you choose the latter, you'd need a suitable transformation extraction and transformation prediction mechanism. So this research seeks to answer the question, can the STN be extended such that transformations are calculated only for the region of interest of the frame, and thereby improve computational efficiency of the models without sacrificing the quality of the generated frames? So in this field, the related work can be summarized according to the criteria discussed prior. The important aspects to pick up on are the time series model. It could either be a CNN, an RNN, or a combination of the two. For example, it could be a 3D convolutional layer or an LSTM or a convolutional LSTM. The next aspect to consider is whether frames are generated from pixel values or from transformations. And lastly, you consider the loss function. The common ways to do this is either through adversarial loss, in which a GAN is implemented and two networks are pitted against each other, basically improving each other until equilibrium is reached. Alternatively, pixel-wise loss functions such as mean squared error or L2 loss can be used instead. The evaluation of these models is still an open problem due to the multimodality of the solution. Existing work uses either quantitative, qualitative, or a combination of approaches. In quantitative metrics, you have things like structural similarity indexes, which accounts for the perceptual differences within a frame. In qualitative metrics, you have a modified Turing test, namely the two alternative force choice tests. The human subject is presented with two options and asked, which of these do you prefer more? Most of the existing work uses a combination of the approaches such that the model performance can be concretely and robustly visualized. Okay, so the modeling of our solution. Our model was based on the model implemented by Finn et al., except the input to this model was simply a 5D tensor, and there was no action or state variables given. And further, the STN was modified such that it only calculated transformations for the region of interest. So the convolutional LSTM layers, there were 7 of those. The output of layer 5 was input into the good STN, which calculated transformations for different aspects of the frame. And thereafter, these aspects were merged to produce a single future frame. Now we consider a traditional STN. The traditional STN would take this entire area and calculate the transformation for it, including the static areas. So if we implement a simple object detection algorithm, in my case, it was using the good features of the frame calculated by the Shi-Tomasi corner detection algorithm and drawing a bounding box around it, we can then narrow down the area over which to calculate transformations. And that is hypothesized to improve computational efficiency of the model. So our aim was to determine the efficacy of the good STN as compared to the STN. So the convolutional LSTM good STN was compared to its ablation. We've seen this model in figure 3 previously. In terms of parameter tuning, the learning rate was determined by the cyclical learning rates for neural networks proposed by Smith, and it was found to be 5 × 10⁻⁴. The beta values for the Adam optimizer were the same as those recommended by literature. The models were trained and evaluated on the KTH action dataset, and the train test split was 65-35. So the models received 5 context frames and were tasked with generating the next 10, and they were evaluated in terms of their ability to generate photorealistic future frames that represented motion. In the study, we used both quantitative metrics, mean squared error, peak signal to noise ratio, and structural similarity, as well as a side-by-side visual comparison. The frames generated were then compared to a baseline of copy lost, which is basically just the last frame of the input copied over and over again to fill up the future sequence of frames. The models were further evaluated in terms of their computational efficiency, namely the training time required for each model. So for some results, quantitatively, as you can see, the convolutional LSTM STN performs the best, narrowly followed by the convolutional LSTM good STN. The margin between the two is quite narrow. For example, on mean squared error, this performs better by 10%, while for structural similarity index, it performs better by 1.35%. And the copy loss baseline performs the worst, which seems to indicate that the models both produce photorealistic frames and created motion that was detectable. A further analysis was done to see how the quality changes as more and more frames are predicted into the future. As seen here, the quality sharply degrades after the second frame is predicted. This is because the model now has to make predictions based on predictions, and errors are sort of propagated through the model. And this is also seen for the peak signal to noise ratio and the structural similarity index. Now, qualitatively, we do a visual side-by-side comparison. In this case, it can form sort of like the two alternative forced choice test. There are three options presented, and you can make a choice on which one you prefer. So I will just reveal which one is which. Option A is the real sequence. Option B is the sequence generated by the convolutional LSTM good STN. And option C was generated by the ablation, the STN model. So there's not much of a difference, if any difference, between between B and C. And perhaps on a good day, it might even fool the reader into thinking it is a real sequence between A and B. So that's how it was qualitatively evaluated in our work. And in terms of training time, both models followed a similar training trajectory. There were significant fluctuations throughout, and training was considered to be complete at this inflection point here, and the inflection point for the gray line as well. And it's seen that the convolutional LSTM good STN requires 3/5 the number of epochs as its counterpart. Now, what this translates to in terms of actual hours, we see that this model required 12 hours more. So the number of parameters were also the same. So the models are similar. Sorry about that. Okay, so conclusions and future work. So we basically tried to test the efficacy of the convolutional LSTM good STN against its ablation. Both models performed approximately the same on both evaluation metrics, but the good STN enabled a shorter training time. A further conclusion that can be drawn is that the frame quality degrades over time as predictions are made on predictions. In future work, we'd like to extend the qualitative evaluation to be more robust and use the two alternative forced choice test. And also we'd like to train the model in a CGAN architecture. So thank you very much for your time, and I look forward to answering any questions that you may have.